Hey guys, today we'll continue in our series where we go through the courses in FPGA Academy. Today we'll try to implement this design. This design is part 3 in the second lab. If you haven't watched first part and second part, you can watch them on my YouTube channel. And today we will continue with part 3. Figure 2a shows a circuit for a full adder. This is full adder, which has the inputs A, B, and C, and produces the outputs C and C0. So we have carry input, carry output. We have our output and 2 inputs. And we have the truth table for this circuit. And here we have 4 of these full adders added in parallel, and if we design it like this, we create a 4-bit adder. So we can add A and B, and A and B will be 4-bit. And it's called 4-bit ripple carry adder circuit. So that's what we will try to implement now. Create a new Quartus project for the adder circuit, write a VHDL entity for the full adder circuit, and write a top-level VHDL entity that initiates 4 instances of this full adder. Okay, so I have already created part 3 in our project from the last episode, and now we will create a new VHDL file. We will call it full adder. We will insert template we will insert a template, and we will call it full adder. And full adder will have carry in as input. It will be std logic. Then it will have A as in std logic and B in std, or we can just do it like this, AB. And then it will have S out std logic and carry out std logic. So these are our ports that correspond to these ports. So we have 3 inputs, 2 outputs. Now we will try to implement this design. We don't have to use we don't have to create XOR as we did in the previous part, but we don't have to because Quartus coders uses have XOR implemented, so we can just do S and then C in and XOR and whatever will be XORed with. So in this case, we want to XOR this with the output of XOR between A and B. So A XOR B, and that's our S. So S will be XOR C in, and AB XOR output will be input to this XOR. So this seems to be correct. Then we will create this multiplexer. We have our multiplexer here, so I will just copy this, create a new VHDL file, and call it 1-bit 2 to 1, and we will just remove the vector here and make it Boolean, and let's call it mux 1-bit 2 to 1, and everything here we just change this, and this will be okay. And so let's create component in our part 3. Or first we have to finish the full adder. I haven't saved it, so we have to save this as full adder, and we have to create a component. Mux 1 bit 2 to 1. We will import the ports. Like this, and component. And we want to get the output of this as select here. And so let's create an instance of the MUX. Port map. Here we will put XOR between these two. And we will have B as first input and C input as second input. And as output, we will put it to C0. So this is our design, and now we can use it in part 3. So component for header. Let's copy the ports and component. And now we will create four instances. And we have to also specify our inputs and outputs. So as input, we will have switches. Or are we supposed to write a VHDL entity for the full adder circuit and write a top level VHDL entity that initiates 4 instances of this full adder? Yes, so we will just input switches in std logic vector 9 down to 0, and as output we will show it on the hex, right? Or to the lights. Connect the outputs of the adder to the red lights. So LEDR will be out. Out. And that's the same std logic vector. So you'll use the switches and show the result, the addition on the LEDs. Let's create 4 instances. So full adder 0 will be instance of full adder, port map, and in this case F0 will have Cin as input, and Cin will be switch 8. So switch 8, and we will need 4 signals. So carry 1, carry 2, and carry 3. These all signals. Std logic. These will be our carry signals from one full adder to another full adder. Here we will have as A will be, we will use switch 4. So here switch 4, switch 0, and carry 1. No, first LEDR, LEDR 0. So our S0 will be LEDR 0. Now we can copy this 4 times or 3 times, 3 more times. And this will be switch 7, 6. No, this will be carry 1. This will be carry 2. And this will be carry 3. And this will be switch 5, 6, and 7. And 1, 2, and 3. And 1, 2, 3, and this will be carry 2, carry 3, and carry out. Okay. I think this should work. So we have our top level entity set. You can try to compile. Include the necessary pin assignments. Test your circuit by trying different values for numbers A, B, and C in. We have some error. Okay, semicolon at the end. Another error. Here, semicolon. Any more errors? And here, semicolon as well. Let's try now. Let's see if we have. Okay. And carry out. Oh, yeah, carry out will be in our case. Carry out will be another, so that will be just LEDR 4. Finally, it's correct. And in the next part, we will try to show it on the hexadecimal as a BCD, represented as a BCD, binary coded decimal. So in this case, we are using LEDs, and in the next next part, we will use 7-segment displays. Okay. We have compiled. Let's try to program. I want to open this. No hardware. I have to connect my board. Okay. Now we can program. So in our program, we have these are, let's look at the design. Switch 0 and switch 4 and switch 0 are the first binary, are the first bits of the binary numbers. So if we switch 0 and switch 4, we should see number 2. So that's correct. We see number 2. If we switch, for example, if I switch number 2 if I if I turn on switch number 2 and number 1, that gives us 3, because binary 2 and binary 1 gives 3. So we can do a simple addition. So this seems to work. This seems to work fine. The carry also seems to work. So basically, if we 4 what did we set as carry in? In our case, carry in is switch 8. So this is the maximum that we can carry in is switch 8. And we can see that now we show 4 LEDs plus the carry out. So this design seems to work correct. And let's continue. We'll do part 4. So let's create a new HDL. We will copy, or yeah, we will copy part 3 and save it as part 4. We will set part 4 as top level entity. And let's read what we have to do. In part 2, we discussed the conversion of binary numbers into decimal digits. For this part, you are to design a circuit that has 2 decimal digits, x and y, as inputs. Each decimal digit is represented as 4-bit number. In technical literature, this is referred to as a binary coded decimal BCD representation. You are to design a circuit that adds the 2 BCD digits. The inputs to your circuit are the numbers x and y plus a carry in Cin. When these inputs are added, the result will be a 5-bit binary number. But this result is to be displayed on the 7-segment displays as a 2-digit BCD sum. For a sum equal to 0, you would display 0. For sum of 1, 1, and so on. For 10, we will show 10. Note that input x and y are assumed to be decimal digits, which means that the largest sum that needs to be handled by this circuit is 19. From part 3 to produce a 4 from part 3, so what we have just made. Let's create a new entity and call it ripple carry adder, or just adder. Let's call it adder. We will call it we will take part 3, copy, and we will call this 4-bit adder, or adder 4-bit. Adder 4-bit will take a number, binary numbers a and b as inputs. They will be 4 bits, and as output we will get s 4 bits, 4 bits, and then we will have carry out as std logic, like this. So we have to just, instead of switches, we will, here we have so A0, 1, 2, and 3. We will have, here we will have B, here we will have S, and this will be carry out. Let's save it. Adder 4-bit. And this will be carry in. We need one more carry in. That will be in and in. Okay. So we can use this. So we have our 4-bit adder, and create a new project for a BCD adder. You should use the 4-bit adder circuit from part 3 to produce a 4-bit sum and carry out for the operation x plus y. A good way to work out the design of your circuit is to first make it handle only sums that are smaller than 15. With these values, your circuit from part 2 can be used to convert the 4-bit sum into 2 decimal digits, S1 and S0. Let's look at part 2. Here we have designed this circuit, so we can use it. We will look at part 2, and we will have to also change this. So let's copy this, create a new VHDL file. We will call it bin to binary to decimal, and as outputs we will have hex 0 and hex 1. So it doesn't get confused with the bin assignments. So I will call it segment 0 and segment 1, and as inputs we will have binary number, bin num, and the binary number is supposed to be 5 bits, right? Five-bit binary number. Yes. So this will be 4 down to 0. Should we include? I think this should be just. Let's call it 5-bit binary 5. Oh, let's keep this as it is, but as output we will have number 0 and number 1, and they will be 3 down to 0, or we can call it BCD num and BCD num 1. Let's change the design. We don't need the 7-segment displays, so we will remove those, remove the component, and we have our comparator. Our comparator will take binary number. Our circuit A will also take binary number, and our MOOCs. And our BCD number 0. Our BCD number 0 will be output from MOOCs. So it will be this. And input will be here, binary number again. And our BCD number 1 will be zeros and Z, or Z signal. Okay, so we have created our binary to decimal converter that only works with numbers until 15, so less than 16, but only sums. We will fix that later, and we can test it. We can test it now. So part 4, we need to import our binary to decimal converter as component. Like this, and component we don't need this, and we don't need this. And let's see what we want to do now. We want to add so we will use the same switches as last time, and we want to add them. So we can basically copy the code from, or no, we will create new instance of full adder, or we don't need full adder, we need adder 4-bit. Adder 4-bit component and component, and we will create instance of adder and instance of this port map. As carrion we will use switch 8. As number A we will use switches 7 down to 4, and as B we will use 3 down to 0. Then we have our carry out, and our carry out is just the, we don't need carry out actually. We will just take, we can remove this, and this will be 5-bit. So S4 will be our C4 or carry out, and carry out will be another signal. Like this. Which means that in our design adder will change. So our adder will, let's create a signal called sum. It will be std logic vector 5-bit, and adder will output the sum to this signal, and then we want to display this using bin to decimal. So let's create an instance, bin to decimal port map, and this will take sum as input, and we will need our number to 7 segment display, you'll need this component to display the numbers. So let's create segment 0. Will be instance of this port map. We will create 2 more signals. There will be BCD 0 and BCD 1. So our bin to decimal will convert this number to 2 BCD numbers, BCD 0 and BCD 1. And then in our 7 segment displays, we will display these 2 numbers. So here we will input BCD 0 and show it on hex when we need to have hex here 0 to 6. Let's copy this one more time. This will be hex 0, this will be hex 1. So hex 0, and we will show the other one on hex 1. So first we take input from switches with carry in and show or output it to sum. The sum will be transferred as input to binary to decimal that will split it to 2 numbers that are from 0 to 9, and we will show these numbers on the hexadecimal 7 segment displays. Our part 4 is the top level entity, so we can try to compile. There will probably be some errors, but we can fix them. Semicolon. Let's see if we have any errors. Okay, bin number is, so comparator gets as an input comparator gets 4-bit and this is 5-bit, and this number, yeah, so we have to create a comparator 9 4-bit. Let's add a new VHDL file, comparator 9 4-bit, and this will take as an input 5 bits. Wait, 5 bits? 5 bits. So it should be called 5-bit. Let's save this. Save as 5-bit. I will remove this from project. How did I? File, save as 5-bit. Yes. Comparator 9 5-bit. And it will be the same. Or and So here you'll just put OR and bin number 4. So if bin number 4, if the most significant bit is 1, then Z1 will be 1. So that's all you have to we had to do. Let's go to part 4 and change our header for, or where was it? It was in our binary to decimal converter. So 5-bit here is to be comparator 5-bit, and now it should work. And circuit A has the same problem. Because this whole design was... Yeah, we will have to create... Even the MOOCs has to be... Okay, let's create all of these again. VHDL. This will be 5-bit. It will take 5-bit numbers. 5-bit. So that's all. Call it MOOCs. 5-bit 2 to 1. Let's create a circuit A. Copy this. New VHDL file. Circuit A 5-bit. 4. And this should output. If you look at our numbers, if we input here 1, but we want something that is smaller than 9, then this should just be 0. So we can put 0 here and it like this. Let's call this circuit 5-bit. And in our this is in our binary, we'll change these to 5-bit, 5-bit, and 5-bit, 5-bit. Okay, let's try it out now. So this is to be 4, this is to be 4. Okay, we have to change all of these to 4s. And BCD number, it has to output. Oh yeah, we didn't have to change the MOOCs, because here we take as an output, but here we want just so. How do we do this? Our MOOCs can stay 4-bit, but we just, oh yeah, everything can stay 4-bit. We just don't input the comparator. No, comparator has to get, and circuit A will have to change later too. So yeah, only this can stay 4-bit. this can stay 4-bit. So our MOOCs will get binary number, but it will get only 3 down to 0 from the binary number, and A signal will stay 3 down to 0, and circuit A 5-bit will output, it will take as an input binary number 5-bit, but it will output 4-bit, like this. So let's go to part 4. And here I want to go to binary to decimal. Circuit A will output 3-bit, MOOCs 4-bit, 2 to 1. That's correct. Okay. Let's see if it has any problems now. Okay, seems to work. So right now we should, if we display anything between 0 and 15, or if we display any sum that is between 0, the sum will be between 0 and 15, we should be able to show it on the hexadecimal displays, on the 7-segment displays. And we are doing part 4, so that's this. So with these values, your circuit from part 2 can be used to convert the 4-bit sum into 2 decimal digits. Yes. And let's try to program. So first I will try to add 1. So you can see I added 1 and 1. Let's try to add 2 and 2. That's 4. Let's try to add 2 and 3. We can add, for example, 7 to 1, 7 to 2, 7 to 3, 7 to 8, 7 to 4, 7 to 4. 7 plus 8, that's 15, yes. So you can see 15 here. And if we output anything bigger, you can see that it's invalid. It's invalid right now. So 15 is the highest number. So this seems to work, and now we will try to add. Sorry. Now we will try to add or be able to add numbers or get the sum that is between 15 and 19. Then once this is working, modify our design to handle values of 15 or between 19 and 15. One way to do this is to still use your circuit from part 2, but to modify its outputs before attaching them to the 7-segment display to make the necessary adjustments when the sum for the adder exceeds 15. Write your VHDL code using simple assignment statements to specify the required logic functions. Do not use other types of VHDL statements such as if-else or case. Yes, we are not using those. Use switches for the inputs and use switch 8 for the carry in. Yes. Yes, carry in. Display the BCD value on the 7-segment displays. Since your circuit handles only BCD digits, check for the cases when the input is greater than 9. If this occurs, indicate an error by turning on the red light. Okay, we'll do that later. So now we will try to implement this part. If you look at numbers, so right now we are working until 15. If we go to 16, we can see that the 5th bit turns to 1. So we will use this and we will in our where is it, circuit A bit, we will add width with a with binary number 4, which is the 5th bit. If it select a out and we will select this output if this value is 0, and I'll look at the syntax. Okay, some colon, and we will take a different if it's 1. So if it's 0, if the 5th bit is 0, we will keep the same output, but if it's 1, we will change the output, and we will changing in the following way. We can see that the least significant bit is the same, so that's the same as here. We can copy that. The second least significant bit is inverse, and the third bit is the same as the second. So we will just use not. We will take this and copy it twice. Yes, like this. So we got the 3 bits. Then we will the 4th bit will be a little trickier, I think. Here it's 1 and here it's 0. So that's the same but not inverted as the bit 1. You can see that these the first bit corresponds to the 4th bit. So here you have 1 and here 0, and the final bit will be just zeros. And yes, so like this, we have 1 2 3 4, 1 2 3 4 5, no, 1 2 3 4. So we have four. We can simulate this. So now we will simulate it to see if it's correct. So we will set this as our top level entity. We will do analysis and synthesis. There's an error. I have with select when. So here I have to use when. Okay. Let's try it out. And I will again have to use this part for the simulator. Okay, we didn't get any errors. Let's open the simulator and we will delete this. Yes, we will insert nodes. This seems like our this seems like our inputs in our circuit A. So you have bin number and A out. This is input. Again, for this we will do count as we did last episode. We will count every 1 nanosecond. So we have values until until 19. That's what we want. And now we want to go to simulation settings, reset default. And here I have to change the code. So save it and we can try to run it. And we have our simulation. So let's sign. So until 9 we don't care. And here we can see that we have 0, 1, 2, 3, all the way until 9. So our design is correct. So we get just the first digit from this 2-digit number. We get just 0, here we just get 1, here we have 6, and we get 8 and 9 here. So that's great, this is correct. We can close this. And that's it for part 4. So we can set a top level entity. We might want to we might also want to add this. Since your circuit handles only BCD digits, check for if it's greater than 9. And if it occurs, indicate the error by turning on red light. We can do this. So we will do it in our part 4. We will get LEDR output as STD logic. And we will use our comparator 9. And yes, we will use our comparator 9. And how do we do this? Yes, I know how to do it. So we import the comparator, not this one, we want this one. We import another component. Import it, and we will create two instances. Comparator 0, port map. It will take as an input this, and as output we will create two signals. It will be called over BCD, which means it's over the BCD value, over BCD 0 and over BCD 1. And create one more. We'll assign the outputs to them. Here we 3 down to 0. And we can now LEDR 9 will be this or this. So if X or Y is greater than 9, we will turn the let R9. There's probably a better way. We probably can just use unsigned and if or something, but since we have our comparator, we made it in the previous part, we can use it. And we can also probably display which which one is over. So if number 0 is over, we will show it on here, and if it's this one, we will show it on lat 8. So we can compile it. We have correct S. There is some error. semicolon. And now we should be able to add two BCD numbers, which means numbers from 0 to 9, plus 1 carry in. So in total, that gives us the number 19. You can see it here. We have one number up to 9, one number up to 9 plus the carry in. So that's in total 19. So if we switch all of these switches to 1, we should see 19. Okay, let's program. So we see 0. I will now switch all of them to we can see 19, and we can also see that all the 3 lights are turned on, which means that both of the numbers are over 9. So if I just put 9 like this, no, like this, give me a minute. Yes, right now we have 19, and we don't have any of the lights turned on, and we can do some addition. So for example, I want to know what 7 plus 8 is, so I will put 7 here. I will put 7 here. Then here I will put, what did I say, 6 or 8? Let's put 8. And this is not 8, this is 8. 8 plus 7 is 15. That's correct. Let's do 8. Let's do plus 9. You can do plus 10. And you can see that the BCD number is over 9, so that's not correct. But even though it's over 9, you can see that the output is correct. So we have finished our design today, and that's it for part 4. Let's see if we haven't missed anything. Include your recipients and test your circuit. We have done that. And let's see. Yeah, that's it for this part, I think. And in the next part, we will look at how to do what we have done today, but in using if and else. And finally, we will learn how to convert 6-bit binary number to 2-digit decimal number. So instead of 4-bit, we will convert 6-bit binary number. Okay, that's what we will do in the next episode. If you want to see it, don't forget to subscribe, and I will see you next time. Bye.